So we now officially start module 3. I realize that we don't have enough time to start this, but next lecture, we have a guest lecturer. So I want to kind of quickly go over enough things. If you want to just read more, last year we have 2 lectures on this. You can watch the 2 lectures from last year, which will help you better. Because the guest lecture is kind of stand on its own. I want to kind of give enough introduction so you can understand this. I apologize if I have to run a little bit over time. You can feel free to drop off, but I just kind of want to make sure that people are roughly prepared. So in our genomes, we mentioned that you and me, every 2 people, we are very, very similar. 99.999 similar, but there are occasional differences. And some of those could be quite common. For example, in one location, maybe 80% of the population have a G and 20% of the population have a T, in this case. Well, so here it's like 95% G, 6% T. This is a single nucleotide polymorphism, which is different between the population. So here we want to define that this location is called a locus. The plural is the loci. And in this location, because they have either a G or a T, we say it has 2 alleles. Allele means the possibilities in this location. And so it means in this locus, we have 2 alleles. G is the major allele, T is the minor allele. In order for something to qualify as a polymorphism, the minor allele frequency needs to be over 1% in the population. Otherwise, we call it a rare variant and not really polymorphic, okay? And in the genome, most of these polymorphisms are single nucleotide polymorphisms, which is this single nucleotide difference between populations. This usually initially comes from DNA replication mistake. So it's, say, when a dad, a germ cell is making a sperm, that replication is 10 to the minus 12, I think, error rate. It just by chance, it created that mutation. And that sperm is fertilized to make a baby. And this exists in the population, but for some reason, this particular baby had a lot of offspring. And now it's 1% of the population. It still happens, right? So, yeah, so this the transmitted usually is from germline. And this accounts for, you can see, 90% of the genetic variation. And a very, very important characteristic of the SNPs is that adjacent SNPs might be linked. You can see here, supposedly we have 2 loci. One is a loci. For example, in here, supposedly nearby there's another base, another location. That's the A position, and this is the B position. It's another locus. And then in the A, there's a so by the way, people use capital A for the major allele and the small letter as the minor allele. So in this case, in this locus, supposedly this is locus B. The major allele is G, that's the big B. The minor allele is the 6%, is the T, is the minor allele, is the small b, okay? So things is, because very often DNA recombination, there are crossovers, so things can be cut and transferred to another place. But if there is a SNP and the nearby a SNP, they usually get transferred together when the chromosomes are having crossovers. And so they are linked. So if you have one SNP, you are likely to have another SNP in the same person. And that's called a linkage disequilibrium. And you can calculate this. For example, if a population have, this is one locus, 2 allele. So some people in this one SNP location can have either 2 big A's, 2 small A's, or a big A, a small A. So the big A is the major allele, small A is the minor allele, right? And so, sorry, I'm using B in this case. You can use A as well. Yeah, so, but for example, the probability of a big A is P, and the probability of the small a is q, of course, in this case, p plus q is in the genome, it should add up to 1. But if you look at the overall population, how many people have two big A's, 2 small a's, and a big A, small a? They may not be equilibrium. You can take a look. I think, so it's, let me see, is it always in equilibrium? It's a good question. You can check. I'm not sure actually in the genome. Well, at least PPQQ plus 2PQ, they need to add up to the whole population. The linkage disequilibrium for A and B is when you have two nearby positions. Also, sorry, this is the equilibrium of B. So if you know, 1B is 60%, so the major allele is 60%. The major allele combination would be the P squared. The minor allele square would be Q squared, and these are the others. And if you really observe this, this is in equilibrium. But imagine we have two locations, two loci, A and B, and also each locus have two alleles, big A, small a, big B, small b. You look at the population, on the left side is the equilibrium. You see them together. But sometimes you will see that in the populations, the big A and big B are always together. Small a, small b are always together, whereas the big A, small b, and small a, big B, they are less likely to appear. And so on the left side is what you would expect if things are in equilibrium. It's complete random mix. Whereas on the right side is what you observed. And people can use a chi-square test to look at the agreement, the expected on the left and the observed on the right, to see how much linkage disequilibrium there are between the A locus and the B locus. And if you can see some extreme cases when you always see big A with big B and the small a with small b, and nothing on this side, then the LD will be 1. You know, these are completely linked. And so very often we do see things that are kind of linked. And in fact, so LD is alleles that occur together more often than expected by chance. It just means that these two alleles are usually physically close to each other. They are always moving together. If there are chromosome crossovers, they always move together. And sometimes it's not just two, it can be a whole haplotype block, which means a group, a cluster of SNPs are linked together with very strong LD. And this usually happen in big chunks blocks. And they sometimes reflect recombination hotspot on those boundaries. It could be related to the chromatin structure. Remember tag, domain, and the compartment A and B. It might be related to the chromatin and in the germ cell, in during the recombination. And so basically, because we know within the haplotype blocks, the SNPs are kind of linked. If you know one SNP, you kind of know the other SNPs. So potentially later on, we will see with association studies using haplotype block, you can get more robust results than using individual SNPs. You can get stronger hits. Why do we care about getting the SNPs? You probably know Angelita Jolie had a double mastectomy because her DNA has one mutation on a gene which gives her much higher chance of developing breast cancer and ovarian cancer. And so after she had babies, she didn't want to have that risk, so she can reduce the risk. There's another case where Mike Snyder is the chair of the genetics department at Stanford. He had his DNA tested. At the same time, he's kind of monitoring himself for a number of day-to-day physiological variables. And interestingly, his DNA test came back suggesting that he is more susceptible to get certain disease like type 2 diabetes. And as people were monitoring his physiological measures, they say, oh gosh, they can actually see him about to start kind of a early onset of type 2 diabetes. And so based on measurement and also based on the genomic predictions, Mike is now living a lot healthier, exercising or eating the right things, eat less sugar. And so I think knowing your germline does have important influence on your lifestyles, how much you do screening for diseases. And also, by the way, SNPs influence how different people respond differently to a drug. And so in order to really do this well, there are a lot of these genome-wide association studies done. There are two types of these studies. The first is family-based association studies. And so in these studies, usually you get two parents from same trios, families of parents and a child, always profile the affected child, and the parent may or may not have the disease. But they know that the child is affected. And so in this case, they just look, for example, and then they do genotyping. By the way, early days, people do genotyping with SNP arrays. So in each array, in each locus, you know what is the allele for mom, dad, and what's the allele for child. So you know the genotyping. And so in this case, but recently people are also doing either whole exome sequencing or even whole genome sequencing now, because genome sequencing is like close to $1,000 a sample now. You can do genome sequencing, and then in each SNP location, you look at what is in the one parent, the other parent, and what is in the affected child. And then in this case, by the way, the first parent actually does not have information, because we know for sure the first parents have to give a big A to the child. But the second child, the fact that we observe that the child have two big A's, it must mean that the second parent transmitted the big A to the child. So the really informative transmitted allele is the big A. We don't really care about the non-informative transmitted allele. And so this is one family. Then we look at another family of trios. The parent is a big A, small a, another parent also big A, small a, and the third one is the child is also big A, small a. So in this case, we know, any allele is possible in here in many combinations. So, but the transmitted allele, some big A has to be transmitted here, but the small a has also be transmitted for the child to get it. And the third family, the second parent is not informative. The first parent is informative, because we know that this big A has to be coming from that first parent. So the transmitted allele is A. The fourth family has no information. The fifth family, we know that there's a decision made. Well, we know that in the first parent is the big A that's transmitted. In the second parent is also the big A that's transmitted. So there are two big A's transmitted in here. Next one is the big A that's important. This one has no information. Next one, it's the small a that's important. This one, the first parent has no information, and so on. So also, you always look at the informative allele that's transmitted. And at the end, you ask, in this particular locus, let's look at all the transmitted allele. By the way, these are all the children that have the disease. You look at some, disease, and you ask, what are the transmitted the allele versus the not transmitted allele. By the way, these two numbers are always zero, so it doesn't really matter in this case. Whereas here, you are asking, what is the count of the transmitted allele for the basically, if you transmitted the small a, then you didn't transmit the big A. How many small A's do you get? How many big A's do you get? Versus the expected, if this SNP has nothing to do with the disease, big A and small a should have equal chance of being transmitted to the child. Whereas if you see this type of really unbalanced big A being very dominant transmitted into the child that have the disease, that's an indication that this allele might be related. This allele at this locus might be related to the disease. And that's how you find associations. Okay, and so for family-based association study, we look at this transmission disequilibrium test. And we only look at those parents that have heterozygous parents. The non-heterozygous parents don't really matter. You calculate the observed over expected using this table. C is basically how many small a are transmitted. B is how many big A are transmitted. The other AD are zeros. And you look at the expected versus the observed. And from this, you calculate the chi-square. It will tell you whether it's significant. And you do this across all the SNPs, all the SNP locations in the genome. Do we need to worry about multiple hypothesis testing? Do we need to worry about, you can speak up, it's okay.
I think we should worry about if we are like testing like multiple alleles, say like A, B, C, yeah, C. Let's say we have 3 alleles, and we should do. But if it's just one, we don't need to.
Yeah, because for this, if it's only one allele, you don't need to. But really, anytime people do a family-based association study, they test all the, because you look at all the SNPs in the genome. Usually there is a SNP, I think every 1,000 base pair. And so across the genome, you're doing kind of 1 million tests. So that's why you do need to look at multiple hypothesis testing correction. And because there are millions of tests, you usually need to use a very, very small p-value in order to get a decent FDR. But the more popular approach is a case control study. You just get population. You get a group of people with the disease and a group of people without the disease. If you're doing this well, you need to make sure that the two groups are roughly matched in their distribution in terms of age, gender, racial, and potentially lifestyle, roughly comparable. And then you look at the SNP, you do the either the SNP typing from arrays or from sequencing, and then you ask, okay, in the cases, how many times, so supposedly this is one locus with 2 allele, either a G or a T. You can look at the cases, how many times you count a GG to appear in cases, GT in cases, TT in cases, right? So this homozygous is TT and GG, heterozygous is GT. In the controls, you also calculate, how many are GG, GT, and TT. And then we ask what allele are really present in the cases. And so in the cases, it's because if it's GG, there are 2 R zeros because G appear twice. So you count that as 2. And in this case, R1, you count as 1. Right? Whereas the T is once in R1 and twice in R2. Right? You just ask how many times these type of alleles you observed, the G allele versus T allele appear in the cases, and how many times do you see it in the controls, right? And if you know that the whole population overall has how many Gs and how many Ts, you can ask what is the expected, and also how how many cases you have and how many controls you have. You can calculate your expected observed Gs in a case, Ts in the controls, and so on. So we have a question in here. Can you what is, transmitted? The transmitted disease in this case is the transmitted allele that's important. So for example, in the parent-child case, we know this parent has 2 big A's. Yes, it is transmitted. For sure that big A has to go to a child, but it's not informative because this parent, that sperm didn't actually have to make a choice. It's always big A. Whereas the other parent, or maybe an egg in this case, because it can make a big A germ cell. It can also make a small a germ cell, sorry, the sperm or egg. You know that the fact that the child has a big A, there is a decision that's made. The big A came into this child, and that potentially is the reason the child have disease. For sure, the other A, it's always the big A. And so we only look at the informative transmitted allele. The other one, in this case, both parents give big A, well, the child has no chance, so no selection is done. So in this case, it's not informative. We don't look at this as transmitted allele. Yes, it is transmitted, but it's uninformative. Okay. In this case, there is no transmission. We're just looking at, you just count how many times G appears in case, how many times T appears in the case, how many times they appear in the controls. And on the right side is the expected, and the left side is observed, and you again do chi-square test, and you calculate the p-value. Do we need to do multiple hypothesis testing? Yes, you do. Again, we're testing every locus. So it's basically GWAS studies is like a million chi-square tests. And then so you do need to look at the FDR. But as we mentioned, if you have to do a million tests, remember, if you remember the RNA-seq differential expression, the more hypotheses you have, your p-value has to be even smaller for you to maintain the right FDR. So you have to have an even stronger criteria to call something. And so with GWAS studies, because you're dealing with like a million SNP locations, loci in the genome, your p-value cutoff has to be really small in order to make your FDR less than 0.05. And so one way to reduce your total number of hypotheses is to look at just a haplotype, because it could be that these 10 SNPs from previously, people have done enough studies, also in your patient, you can see that anytime you have these SNPs, the nearby SNPs are, if they are completely linked, then it's a block. You don't need to test them multiple times. You just do a block. It's a one, instead of say 10 SNPs, you test as 10 times, you just do one test, because it's just either this or that, right? Then it's easier if the 10 are linked. And so with your reduced multiple hypothesis, you still, the chi-square test is kind of similar. You have fewer tests, and so the p-value cutoff can be looser, but you still have the same FDR. And by the way, in terms of disease association, in addition to getting the p-value, we also want to know the odds ratio, or also something called the effect size. You can imagine here, this type of chi-square test, even if the case and control has tiny difference, if you have a huge population, we're testing everybody in the US, 300 million people, even a tiny difference will give you a significant p-value. But maybe it's like a fair coin, unfair coin. If we do a million coin flips, maybe you will know that the coin is not fair. If you have a very significant p-value, that is an unfair coin. But the head and tail is not a 0.1, 0.9. It's only a 0.4999 versus 0.50001, right? So that's only a tiny bit difference. And so in addition to knowing a p-value of this difference, we also need to know the effect size, or how strong is this SNP in terms of getting you a disease. And that's done by odds ratio. And so if you look at the cases, how many how many times G appears in the cases versus controls, and in the T allele, how many times it appears in the cases and controls. The odds ratio is basically the AD divided by BC, and that will give you a score. If it's 1, it means there is no disease association. If it's larger than 1, it means that the allele in C is really, sorry, in this case, is larger than 1. In this case, this allele is increasing the disease risk. Whereas if it's less than, sorry, if it's less than 1, it means that when you have this G allele in the cases, it's less likely to have the disease. And so even if your p-value is huge, if your odds ratio is only 1.001, that's not a very serious thing. It's like, oh, if you have this, you are 1,000th of a chance more likely to get a disease than another person with a different SNP. No big deal. For you know, like the SNP that Angelina Jolie had, like breast cancer, I think that one, the odds ratio is probably like 2. It's twice as likely to get the disease than the other. That's much more important. Okay. Yeah, so sorry, this is actually coming from the previous one as well. So in general, for GWAS studies, you always want to do multiple hypothesis testing. Okay, questions? Most people nowadays do GWAS using this case control studies. Yeah, I think for that you have to calculate this SNP versus the other SNPs. Every time you do A versus not A, C versus not C, T versus not T. Okay. Because at the end, you want to ask whether this guy have this SNP, whether he or she is less likely to have the disease.